Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we were talking about a simple pendulum. We said a simple pendulum, it is a mass that is attached to a string that it moves back and forth around the equilibrium under the effect or the influence of gravitational force, and it shows the periodic motion too. And then we said in pendulum, the restoring force, that is a component of gravitational force. But if you remember, we've divided or we've resolved the gravitational force into two components. One of them were perpendicular to the direction of the pendulum's path, and the other one was tangent to the direction of the pendulum's path. And if you remember, we said that the component that is tangent to the direction of, or to the direction of the pendulum's path, that component that is called the restoring force in a pendulum. So we can say restoring force in a pendulum, it is a component of gravitational force that is tangent to the direction of the pendulum's path. Don't forget this. And then, of course, we've talked about like how are these, or how the displacement, the restoring force, the acceleration, the angle theta, the velocity, the kinetic energy, the momentum were changing once a pendulum is swinging back and forth. And then we ended up right at this point here. So this is the last thing that or we stopped right at this point here. Now today we'll talk about the energy conservation in a pendulum. Remember this. Before we begin with this, just remember, or I would like you to know that all the cases or all the situations that we're using a pendulum and in physics, we consider the system is ideal. When we say ideal, we assume that there's no friction, there is no air resistance, because once we say this, now the energy is conserved. Otherwise, because of these, the energy will not be conserved. So remember this, the energy or these systems that we're studying, of course, like a pendulum, these are considered as an ideal where no energy is lost. All right, Zerbash. So this is basically what we have or what we're going to study. The first thing that it is the energy conservation of, or you can say in a pendulum. But before that, let me draw something for you and tell you how this diagram never been in Uzari, but I'll tell you there's a way that it could be possible. It could be in Uzari too. So let's start with this one. Here we have a pendulum, and we know that this is the equilibrium position. And then let's say here is a pendulum. This pendulum is going to swing or start swinging from point A, and we can say this is point B all the way to point C. So it can be at this location to here at a certain time here. But if you remember, we said in a pendulum here, when the mass is at largest or maximum displacement, what is the energy of a system? Do you remember this? We said the energy at maximum displacement, so you can say x is maximum, or this angle theta, it is the largest, Basha. So the energy of this pendulum here, it is elastic, it is gravitational potential energy here. Okay, what happened when you let go of this mass that is starting to swing, Gwanya? So we said the energy of the system is conserved. So when this mass is right here, all that potential energy, it is going to be converted to what? To kinetic energy here. So that is that is when it is moving towards the equilibrium position. All right. So what happens when the mass is leaving the equilibrium position? Now you can see that the height is going to increase. And guess what happened when the height is increasing? So of course, we know that this time, this kinetic energy here, right, it is going to convert to potential energy here. But let me give you perhaps maybe some numbers, all right? So don't forget this. We said at this point here, we have maximum potential, by the way, maximum potential gravitational potential energy. Here, all that potential energy has converted to kinetic energy, and then once more time, here this kinetic energy, it is going to be converted to gravitational potential energy as well. So now let me give you some numbers, right? Okay, assume that the potential energy of a system here, it is 100 joules, because it is energy, so it is measured in joules, Basha, and it is maximum. So at this point here, we can say all that potential energy, it is, or all that joule, all that energy, it is gravitational potential energy at the maximum displacement from the equilibrium. Basha, when this pendulum is swinging towards the equilibrium, now this potential energy is going to convert to kinetic energy. Once the mass is at equilibrium, all that 100 joule, it is going to be converted to kinetic energy. So now the kinetic energy of the system, it is 100 joules, and it is solely kinetic. Yani it is only kinetic or there's no other energy here? What about when it is going, for example, towards point C, as it is kind of like going more and more? So at point C, it is going to stop. Yeah? So at this point here, all that kinetic energy, we can see that it is transferred or transformed into gravitational potential energy here. So now here's the 100 joules again. We assume no energy is lost in here. What about if we take a point right here? At this point, we can have both kinetic and potential energy. So if it is a midpoint between point A and B, we can say 50 kinetic and 50 potential. That would be a total of 100. So once again, how can we explain this using a diagram? So here we have a diagram. Basha, this diagram, it is about, we can see that it is about the energy, and you can also say this would be versus the time or different displacement at each one of these points here. So we can say this is the energy, okay? Energy, all right? And this, of course, we're going to take 3 points here. That would be point A, and here's going to be point B. Let's just call it B, small lowercase, and this is point C. And if you notice here, all right, we're going to draw some lines here. Now, at this point here, when the object or the pendulum, the mass is at point A, since we use capital letters, let's use capital letters too here. Okay, so when the mass is at point A, what is the energy of the system? It is solely or only gravitational potential energy. And how much is it? Let's just assume that it is 100. So now this is what happened. So this, we're going to draw a line for the potential or gravitational potential energy. So at point A, you can see that it is maximum. But guess what happened when it is at point B or moving towards point B? This energy, it is going to decrease until it becomes what? Until it becomes 0 at, this is not a very good line, but sort of something, this is what it happens here. All right, so at point B here, it is going to become 0. Maybe this line should touch the ground, all right, but that is totally fine here. But what happened as it is leaving point B, now it is going to increase until it becomes what? Until it becomes maximum again. That is right at point C here. All right, let's say this is point C. So we can say this line represents the gravitational potential energy here. But if I want to draw a line, right, for kinetic energy, how would I do that? Remember, at point A, the kinetic energy of the system, it is 0 here. But what happened as it is moving towards point B? The kinetic energy, it is going to increase until it becomes what? Until it becomes maximum, okay? So at point B here, kinetic energy, we can say, it is going to reach maximum. This is at point B here. But what happened as it is leaving point B? It is going to decrease until it reaches or becomes 0 at point C here. But, so these are the energy or the types of energy that I have. But since the energy is conserved, if I want to take the, let's say, total or the mechanical energy of the system. What is mechanical energy of the system here? It is going to be kinetic energy of the system plus potential energy here. So whenever you start at these lines, for example, if you want to find the total kinetic energy, the total or the mechanical energies of the system, you will see that the mechanical energy of the system, it is always conserved, or you can say that it is 100. I mean, like at this point, it is 100 here. So this mechanical energy, now this line represents the mechanical energy, which is the sum of kinetic energy plus gravitational potential energy of the system here. So if this is 100, the total doesn't change, it is conserved. Basha, so this is the diagram that we have, Basha, never been in Wizari. How this diagram will be in Wizari if they ever ask, they might label these lines. They might say, which one of these lines? Let's just label them here. Let's call this one A. Call this line B here, call this line C, Basha. And then we can have this point here, a point D as well. Okay, so if they ever ask, for example, which one of these lines represent the gravitational potential energy for the pendulum, and how do we know that? Of course, these points will be given. If these points are not given, they will tell you, for example, at maximum displacement. Basha. So we know that at point A or at maximum displacement, the energy of the system, it is entirely gravitational potential energy. Do you agree? Zoe Basha. So now, and it is maximum. So which one of these lines represent maximum amount of energy? Isn't this maximum? So this line here now, it must be for gravitational potential energy here. Which one of these lines represent the kinetic energy here? You can see at point A, kinetic energy is 0. So this line is 0 at point A, so this must be kinetic. If not, there is another way. You can look at point B here. Now, we know that at point B, kinetic energy is maximum, but potential is 0. So if you look at this line is maximum, so this must be for kinetic, and this must be for gravitational because it shows 0 at point B, which is the equilibrium. But they might also say which one of these lines represent the total energy of the system or the mechanical energy of the system. That is going to be this line at the top or this black one, which is always constant. You can see that, or the energy is conserved, we say. And then what about, for example, what if they ever ask for this one? If they ever do, of course, they say if the energy of the system is, for example, half kinetic, half potential, which one of these points is going to be? That is going to be this point. Or at what point, let's say the kinetic energy, it is equal to the potential energy, that is going to be this point. So just remember the diagram, remember the labels, the lines, and things, inshallah, will be easier. So this is all about this diagram that you need to be aware of that. And there's one thing I would like you to do here. Now, this is something extra, but here's what I want you to do if you're using my pamphlet or booklet. This is point A, the one that we just did, and you can make this one point B. There are different labels. I'll show this picture, we've got it online, so I just, use this one without changing this. Basha. So just so that it is more consistent, all right, it is the same as this. This will be point A, this is point B, and you can make this one point C, so you can ignore this point, let's say, case here. So if you can see here, when the mass is at maximum displacement, the energy of the system, it is only potential while the kinetic is 0. At this point, that is the equilibrium position, the potential is 0. Kinetic energy is the same as potential energy, which is maximum, so kinetic energy is, or you can say all that energy is converted to kinetic energy. Once it is leaving the equilibrium, going back to point C, potential becomes maximum again, while kinetic is 0 because the velocity of this mass is 0 at a certain instant, Basha. What else do you need to know? What if it is at this point? You can see that whatever the energy of a system, at this point here, it is going to be somewhere in between the two. If the total is 100, so this point is going to be sort of like 50-50. I hope you understood this. All right, so keep an eye on this for Wazari. Now we have few Wazari questions to solve before we move on to the section review here. It says what? When vibrating, the simple pendulum bob reached to the maximum, Basha. It says, reaches to the equilibrium position. Which of the following values are maximum? So here are a few things I need you to be aware of them, Basha. So it says when vibrating a simple pendulum, so we have a simple pendulum bob. It says reaching equilibrium position. So of course we have different positions there, right? But which one are they asking for here? It says when it is at the equilibrium position, so right here. Okay, so it is not at the maximum displacement. It says which of the following values are maximum? So which one of these are maximum? If you remember the variables or the factors we've studied, it was displacement, it was force, it was the acceleration, or let's say the acceleration we've studied, and then we've studied the angle theta, the velocity, the kinetic energy, the momentum as well. So here's a question, says, which one of these is maximum? If you remember, we said at the beginning maximum displacement, these were maximum, right? And these, of course, were 0. But now at equilibrium, right, these at equilibrium, don't forget, so these will be 0, and those that were 0 now going to be maximum. So now these, of course, must be maximum at equilibrium. So let's see which one of these is mentioned. The first one says gravitational potential energy. Well, gravitational potential energy, should have mentioned that too here. Gravitational potential energy, it is with those. So it is maximum at maximum displacement, but it is 0 at equilibrium, so not this one. Okay, it says the restoring force. Again, if the displacement is 0, the restoring force is also 0, and you do remember this. What about kinetic energy? Very good. We said at maximum displacement, the potential energy is maximum, but at equilibrium, all that potential converts to kinetic, which is maximum here. So we can say this is the correct answer. What about tangential acceleration? Basha, acceleration is with the force if the forces are directly proportional with the force. One, yeah? Again, if the force is 0, then the acceleration is 0 too. I believe you know that one, yeah? Because these are directly proportional. Now the only answer is, or the only correct answer is option B here. Okay, the next question says the restoring force of a vibrating simple pendulum is what? Do you remember we said it is a component of gravitational force that is tangent to the pendulum's path? Zohr Basha. So which one of these do you think it is? It is Fg sine theta. It is totally fine if you see mg sine theta, so this is correct. What about cosine? That is incorrect because if you remember, Gutman, this one is equal to the tangent in a string here. So if I want to do this one here, said if this is the pendulum, Gutman, this is F tangent, which is upward. This is Fg. This Fg analyzes to two components. One of them is Fg cosine, so because these two angles are the same. Okay, so this is Fg cosine theta, and this is Fg sine theta. Gutman, these two are equal in magnitude and opposite in direction. They cancel out. So this one here, this component that is the one that brings the mass back to the equilibrium, so we call this one restoring force, which is Fg sine theta. Zohr Basha. The next thing says, in which one of the following the motion of a simple pendulum, it is simple harmonic motion? Do you remember one of the conditions, or in order to call the motion of a pendulum simple harmonic motion, Gutman, the angle it has to be less than 15 degrees. It cannot even be equal to, then we can call that motion simple harmonic motion. Kawata, by the way, anything less than 15, Basha, it is acceptable, Basha. Anything less than 15. So, but 15 nabi, Basha. In this case, 10. What about 10? Because it is less than 15, so yes, it is possible. What about 60? Too big. What about 90? That is also not true. And then 45, also not true. So, when the angle theta it is equal to 10, of course, that can be considered as simple harmonic motion. Which of these periodic motion are simple harmonic motion, Basha? It is very similar to what we just, said that, but there are a few differences here. A child swinging on a playground that is with an angle 45. This angle, of course, if it is 45, of course, that angle is too big, so we cannot call this one simple harmonic motion. It has to be in a straight line, and in order for the motion to be in a straight line, the angle must be smaller than 15 degrees. We cannot even say equal or smaller. Basha, it is a must. It needs to be smaller. 45 is too big. All right, let me skip this one. Well, actually not. Okay. It says a CD rotating in a player about a vertical axis here. Now, you might say, what about this one here? But listen, in order for something, the question says, which one of these periodic motion is a simple harmonic motion? So imagine if you have a CD disc, Basha, for those who are old enough to remember this. The CD disc, it can be rotating, Basha. If it is rotating, because it is going to repeat the rotation, so this is a periodic motion. But here's the thing. Can we call this one simple harmonic motion? Come on, what were the conditions of simple harmonic? Come on, the first thing, the restoring force must be directly proportional to the displacement. The second, the vibration must be about equilibrium, so it needs to move back and forth, and then back and forth. The third one, we said, the motion must be on a straight line in here. So, do we have these conditions in a CD player or in a CD disc? The answer is no. So we cannot call the motion of this simple harmonic motion. Basha? One of the reasons why, because it doesn't move back and forth, you could say. Basha? This is one of the reasons here. It is going to, let's say, rotate in here. So it is periodic, but it is not simple harmonic motion. Which one of these is periodic? Of course, this would be an option 2 here. Okay, what about C says an oscillating clock or pendulum clock with an angle of 30, that is also not simple harmonic because the angle is too much or too big. An oscillating clock pendulum, when the angle it is equal to 10, we said as long as it is less than 15, so this would be the correct answer. Zohr Bash is that. Now let's solve a few section review question. And by the way, you can see that, or you just saw this question being repeated in Wizari a few times in here. So I got leave it. says, one of the questions says, which of these periodic motions are simple harmonic motion? Once again, all of these motions are simple harmonic motion, but which one of them is, all of these are periodic motions, Basha, but which one of them it is simple harmonic motion? Good man, there are three conditions, so which one of them meets all the three conditions? This one is 45 for a child playing on a swing, so it's the same as if a person is on a swing or on a pendulum with an angle 45. So this is bigger than 15, so we cannot choose this. You do know that. What about this one? Again, a CD disc or a CD rotating in a player. Once again, rotating in a player, it is only periodic, but it doesn't move back and forth. And this motion is, because it doesn't move back and forth, we cannot call it simple harmonic motion, Basha. And then we can also say that, you can see that there is no restoring force directly proportional to the displacement, so that is another flaw or another defect in this, so we cannot choose this. That it doesn't have, or it has actually in this case. So this is not simple harmonic motion. What about an oscillating clock pendulum with an angle of 10? So this is because it is less than 15, so this would be a simple harmonic motion because it kind of like meets all the three conditions we have said earlier on today too. All right, Prasad HD, come on here. What does it say? It says, how does the restoring force acting on a pendulum bob change, Basha, as the pendulum or as the bob swings toward the equilibrium position? That is first part of the question. Need you to know that questions like this are highly, like for example, these are very important or highly nominated for Wuzari to be in Wuzari. And by the way, this been in Wuzari, you can see there is a Wuzari question. They've just kind of like used this or they've converted these two choices, and then you're supposed to answer them. Gosh, let's just scroll this one up a little so that you can see the whole thing. And then here's what it says. It says what? How does the restoring force acting on a pendulum bob change as the pendulum bob swings towards the equilibrium position? So the first thing they're asking about the force. That is first. Second says, how does the bob's acceleration along the direction of the motion change? And then what about the velocity? So they're asking about three things here. They're asking about the restoring force, they're asking about the acceleration, and also they're asking about the velocity as well once it is moving towards the equilibrium, right? It says swinging towards the equilibrium. So now let's talk about, or let me draw the pendulum again one more time and see what exactly or how we could do this, Basha, or answer this question. Okay, take a look. Here's a pendulum. Here's the equilibrium position. And here's the bob or the mass. This mass is going to swing back and forth. So as it is moving towards the equilibrium, we have three factors. We have the force, of the acceleration, and the velocity. At this point here, if it is at maximum displacement, Basha, so the force is maximum. You do know that. Basha, the acceleration is also maximum. What about the velocity? It is 0, right? But as it is moving, let's say, towards the equilibrium, so the force is now from maximum, it is going to decrease to 0. What about the acceleration? It is going to decrease to 0. What about the velocity? It was at rest. As it is moving towards the velocity, that potential energy, it is going to convert to kinetic energy, which makes the mass to move faster and faster, and even the fastest at equilibrium. So we can say, or we can see that as the mass it is moving towards the equilibrium, the velocity it is going to increase, right? Or at equilibrium, you can say maximum. But so what is the question now? How does the force change? We'll say it is going to decrease. Basha, it is moving towards, let's say, the equilibrium, so not exactly at equilibrium. So this force is going to decrease because you can see that from maximum to 0, and it is decreasing. What about this one? From maximum to 0, yani at a point here, the acceleration is decreasing. What about velocity? From 0 to maximum, yani the velocity, it is going to increase, Basha. So this one decreases, but velocity will increase. Bash Baba, remember or keep that in mind. Now, in Wuzari, they were asking about these three variables or factors here. Maybe next time they'll ask about potential energy or let's say about the angle theta, or about the displacement, right? Or about the momentum. It could be anything. So remember to go back to the previous, if you don't know how you can, or how are these changing, to go back to the previous lesson or video lesson and make sure you watch this one so that you can answer correctly. So now let's go back to the question. We said the restoring force as it is approaching the equilibrium, Basha, it says towards swing, there it is moving towards the equilibrium, so don't forget. So we said the restoring force that is going to decrease, Basha. What about the acceleration? That is also decreasing. What about the velocity? The velocity is increasing as it is moving towards the equilibrium. All right, we have another question, which is a critical thing, and it says, when an acrobat reached the equilibrium position, the net force acting along the direction of the motion is 0. Basha, if that is the case, why does the acrobat swing past through the equilibrium? Let me tell you what exactly this question is saying or asking you to explain. We know that if I have an object, Basha, and this object, if the net force, Basha, if the net force on an object is 0, right, there would be no motion, we can say. That is if an object is at rest, Basha. Or you can say if there is no force acting on an object, we normally say the object will not move, yes or no. So if the net force is 0, it's the same as if there's no force acting on this. Basha, if the force is 0, these are directly proportional, so there's no acceleration too. You might just think that the object's not moving too, which is pretty much convincing, right? But this question says, while the acrobat, for example, here's the acrobat, the circus person here, once it is moving towards the equilibrium position here. That is the same as a pendulum here, by the way. When this person is right at this point here, we said that net force, or the force, the restoring force is 0. But if the restoring force is 0, why does the person keeps moving? That is the question, because we know that if force is 0, the object must be at rest or should not move. And yet, we'll say, what thing kind of like keeps moving the object here? So the thing that keeps the acrobat moving here, it is the momentum. Do you remember this, Basha? We've always considering or studying momentum was for this specific reason right here. So momentum, it is equal to mass times velocity, because this object, or that has a certain mass, has also a certain velocity too. So this mass and velocity carries the acrobat, or continues to moving the object past through the equilibrium. This is why it doesn't stop right here. Why? Because we know that momentum is the product of mass times velocity, or you can say it is a resistance to change in the mass and velocity there as well. So because of this momentum, it carries the person while it is at the equilibrium when the force acting on the object is 0. We can say the acrobat passes through the equilibrium because of it has a momentum, or you can say because of the momentum. And the answer will say the momentum of the acrobat carries them past through the equilibrium, and you do know that momentum equal to mass times velocity. This is the equation that I was just telling you about. Basha, we have a pendulum says, how does the restoring force acting on a pendulum change as the bob swings towards, Basha, towards the equilibrium position? It is not at equilibrium, it is swinging towards that point. That is the restoring force. How does the acceleration change? And how does the velocity change? So which one of these do you think you have to choose? Good man, the force decreases, the acceleration decreases, but the velocity increases. So which one of these do you think it is? This one says the restoring force decreased. This part is correct. Acceleration decreased. This part is correct. Velocity increases. So that is going to be option A. Basha. What about the other part? This one says the force increases. That is incorrect. This one says restoring force decreases. That is good. This part, acceleration increase, nakhir, because these two are directly proportional. You don't have to continue. This one says decrease. This part is good. Acceleration decrease. This part is good. But the velocity also decreases. That is incorrect. So that is not option D. Okay, so the only correct answer now, it is option A. They could give you the reverse, by the way. What if they say this time, what if they were asking, like, what happened as the pendulum leaves the equilibrium position? See, this is the mass, right? So now it has just left the equilibrium position. If it is swinging towards the other side here, And if it is moving away from the equilibrium, what do you think will happen? Now, in this case, the force increase, the acceleration increase, but the velocity, it is going to decrease, and then you can have a proper option, then of course you will choose that one. So that is also could be possible. We have something new, which is something very interesting. Now, measuring simple harmonic motion. The first thing we're going to start off with, it is the amplitude. What is the amplitude? Now, previously we've mentioned that in the absence of friction, once we ignore the effect of force of friction and then air resistance, then this pendulum keeps swinging back and forth always, non-stop. And then if we let the mass go at a certain place, then this mass will always go back to the same exact point here. So this is what we're talking about here. By the way, this is a pendulum. You can see that it is a mass, Basha, attached to a string here. And then once you allow this mass, for example, or pull to the side here, then this mass that is going to swing back and forth, back and forth. So this is a simple pendulum, a mass, a string. It keeps vibrating back and forth. But when do we call this, or the motion of this simple pendulum, simple harmonic motion? Gutman, if three conditions are met, Basha. Let me fix this one. All right, sort of. Now here, Gutman, this angle of the swinging, by the way, it has to be so small so that you can see that this motion, it is sort of like almost in a straight line here. So sort of something like this. But in that case, don't forget the other T condition. Gutman, the restoring force must be directly proportional to the displacement, and it must be moving, it must be moving back and forth too. Perhaps I need to fix this one. Give me a second, guys. All right. I'll just move out of the site for a second. All right, I think we almost got it. Yeah, until I fix this one, you can read the definition of an amplitude here. And then after that, I'll start explaining what is amplitude, giving some examples. I think I'm almost done. Right. Okay. Just need one more. God, this took longer than I thought. All right, that is. All right, we're back. So this is, we can say, a simple pendulum here. Just we call it simple because it's really simple. Has a mass and a string. This mass is hanged over something, so you just let it vibrate and it goes back and forth. Perhaps, yeah, don't get hypnotized. All right, so that'll be, let's just give this one here. We'll need it now. So the first thing that we said that we were talking about, that always returns to the same or maximum displacement because there's no energy loss in here. The first thing that we have, it is called amplitude. So we're going to measure these factors here. So once again, the first thing that we have, it is called amplitude. What is amplitude? Now, let me take you perhaps maybe somewhere for a distance from what you're studying. In a calm day, this is the, let's say, the surface of the ocean. You're just sitting, you know, like you're sitting at a shore or watching the ocean. You're basically at a beach, Basha. So you're watching the ocean. The day is calm. So here's the surface of water. But then soon after, let's say, wind starts to blow, and then, you know, like the day, it becomes windy. Let's just say. Then you will see that waves start to generate or the surface of the water is not calm anymore. Okay, so at this point here, these are we can say the water molecules at this. But when the waves are starting, for example, or when waves are generated here, so you can see that the surface of the water is not calm. Some of the water molecules are going to move up, and then some others are going to move down, right? So here's the thing that we say about the amplitude. We'll say it is the maximum displacement from the rest position or from the equilibrium position. What do you mean by rest position? When there was no wind, all the water molecules were here. So we call this one rest position. They are at rest. But when winds start to blow, like I said, some of the molecules are going to move up because of the water. Some others are going to move down. So how much they go up, that is called amplitude. So once again, amplitude, it is the maximum displacement. So amplitude, we use the letter A to represent that. You just remember a keyword here. We'll say it is the maximum displacement. It is what? The maximum displacement. Displacement from the rest position, Masha. From the rest position. From the rest position. That's one way. But look, I need you to be really careful at this point here. This is also a displacement, right? This is also a displacement, but which one of these is maximum? That is this one. So this is called maximum, this maximum displacement, it is called amplitude. By the way, it could be both up or down, doesn't matter. And these are always equal to one another. But we don't say from the top to the bottom. No, from the rest position, either up or down, that is called amplitude. So now this is amplitude, or you can call this one amplitude, Basha. Now let's go back to our topic now. We're studying both mass spring system and pendulums, right? If you remember, here's, let's go back to this. Here we have a spring on a horizontal surface. So here's a surface. Normally, if this string or if this spring is or this mass is not stretched, you'll find it here. So you can call this one the displacement is 0. But what happens once you stretch the mass? Okay, now this pendulum's length, it is going to increase. Of course, you have to extend, but we'll just do that for the sake of the example. So this is what happens. Now, this is where the mass is. How far is this mass from the equilibrium position? We used to call that one maximum displacement, true? Now, this maximum displacement hereafter, we're just going to call this one amplitude, or we'll just write the letter A for that. That is if we have a mass spring system. Basha, is maximum displacement or amplitude, is it only forward? No. If the pendulum or if this mass spring system, it is compressed, it can be the same thing. So for example, now the mass is compressed up to this point, or this is the mass in here. How far is it from the equilibrium position here? How far it is compressed, that you can call the maximum displacement. Now this one can also be considered as amplitude as well. So we'll say maximum displacement from the rest position, from the equilibrium position. That is for a mass spring system. Basha, what about a pendulum? Basha, what about a pendulum? We have the same thing in here. So here's a pendulum. Normally, if it is not swinging, that is where the mass is. So we can say, the displacement is 0. The angle is also 0. But what happens when you allow this to swing more and more, right? It could be at different points, correct? You agree, wouldn't you? So let's just draw this one a bit nicer, maybe. All right, so now how far it goes from the rest position here. We want a nice line here. Okay, how far it goes from the rest position, you can call this one amplitude. By the way, if it is a pendulum here, the amplitude can be measured by the angle theta here. So at this point, there is an angle theta. So that is this line right here, okay? But then if we take this one here, this angle, it is going to be larger than this. So this is if I use displacement, there is a certain displacement here, and then there is another displacement here. You can call it x1 and x2 here. But which one of these is the maximum displacement? It is x2. So x2 can be considered as the amplitude for this pendulum in here. So that is what we call this amplitude. So once again, amplitude is the maximum displacement from the equilibrium position or from the rest position here. Basha, that is the first thing that we have, Basha. And let me not forget, amplitude, that it can be measured in meter, Basha. For example, like this displacement for a spring, it is measured in what? It is measured in meter, right? So the amplitude would be maximum displacement, and this maximum displacement, it is measured in meter, right? Meter. We'll just use the meter. We'll just use the symbol M for that. Basha, what about for a pendulum? For pendulum, the amplitude can be measured what? By the angle theta. And we know that the angle theta that we use, so we can say radian, Basha. And of course, but we mostly use degrees, but you do know that this is the one that it can be used, Basha. But there is one more thing you need to know, that this angle that is measured in degrees, that's the one that we use the most, Basha. It is, these are, by the way, the radian, you can say this is the SI unit, the one that we use to measure the angle for a pendulum, or that is used internationally. When we say the SI, Basha, it is just the one that is, like used for angles here. But we know that radian, it is dimensionless. Basha, don't forget this. Okay, so now don't confuse between the two here. This angle can also be converted into what? Into a displacement, which can later on be measured in meter as well. How? I'll show you inshallah soon. Just remember this. Amplitude, it is the maximum displacement from the equilibrium position. It can be measured both in meter and in radian as well. Okay, of course it can be measured in different other units, but we can say these are the SI units that can be used to measure the amplitude of an object. Basha? Yeah, so this is the definition of the amplitude there. But man, the amplitude of the pendulum's amplitude can be measured by the angle theta, which is between the pendulum's equilibrium position and maximum displacement. Adi mass spring system, but man, it is the amplitude is the maximum amount that the spring is stretched or compressed. That would be the displacement from its equilibrium position. And we also said that amplitude can also be measured in degrees, meters, centimeters, but the SI units are both radian and meter. Now we have two more things. Period and frequency. What is period and what is frequency here? Now I need you to be really careful at this point here. Now, period, we can say it is the time that it takes for one complete oscillation to occur. First of all, let me draw what I mean by this, and then I'll show you this cute pendulum, so-called pendulum here. So here's a pendulum, we assume. So here is a mass at a maximum displacement. So now, what happens if we allow this mass to oscillate? It is going to swing all the way to this end here. We can call this one point A, and this is point B, right? And then what do you think will happen afterwards? It is going to swing back or get back to the same exact location here. Do you know that, or how long it takes, watch this, how long it takes for a pendulum to complete one full oscillation? That is called a period. Basha? So now you can compare this one to exactly one full cycle, by the way. Okay? And this is clearly what a period is. So a period, we can say the time it takes for one full cycle, for one full wave, for one vibration to occur, that is called period, which is how long it takes to go and to come back. That is period. And we know that time is measured in second one, yeah? But that period, it is the time it takes for, remember, for one full cycle, you can say, Basha. Cycle, or you can say for one full vibration. These are the same. And period, it is measured in second, and we use second for that. And also remember, just remember this, Basha. And what exactly do I mean by this now? Now, if you ever want to measure what is the period of a pendulum here, this is what you can do. Watch this. So here is the equilibrium position. Perhaps maybe we can use my tie as a reference point. So this is the equilibrium position here. So that is how how much we pull further back. So how long it takes, Baba, watch this, for this pendulum to go. That is my right at this point, which is going to be your left because you're watching this. How long does it take for the pendulum to start from this point to go all the way to the other point, right? And then back again to the same point. That is called period, don't forget, right? So here's what happened here, right? That is 1 period, 2 period, 3 period, 4 period, and so on and on, Basha. All right, so once again, remember, how long does it take for one full oscillation? This is one full oscillation to go and to come back. That is called period, or how long it takes for this to happen. That is 1 period. Basha, so just assume that, for example, a pendulum, or for a pendulum to swing one complete cycle, let's just say it takes 1 second, Basha. So the period is 1 second. The period for one full cycle, it is 1 second. What if I ask you, how long does it take for half a period? Well, half a period, that is only the time it takes to get to point B. Isn't that would be half of this one? So in this case, period for half a cycle, it is going to be 0.5 second. What if it is for a quarter of a period? That is going to be a quarter. It is this much. Oh, I just remembered one thing, which I'll tell you now in a second. But the next thing that we have, it is the frequency. So what is frequency? We can say frequency is something else. We can say frequency, it is the number of oscillation per unit time. Basha? The number of oscillation per unit time. For example, I'll say, how many oscillations does it make in 1 minute, right? That you can use that to find the frequency, by the way. In other words, how long does it take, or how many waves will there be in 1 second, Basha? That is also another way to say frequency. I'll explain a little bit more, but just remember this. That is, we said this is one full cycle. When you watch this, there's one full cycle. 2, 3, wait. All right, so 1, 2, 3, 4, 5. Imagine if we have, imagine a pendulum is swinging, and we have, let's say, 5 oscillations in 2 seconds. 5 oscillations in 2 seconds. 5 oscillations in 2 seconds, Basha. In 2 seconds. So what would be the frequency here? We'll just say frequency, it is equal to the number of vibrations, or you can say the number of waves, right? These are all the same, by the way. So you can have the number of vibration, or you can have the number of waves, or you can have the number of oscillations. These are all correct, Basha. Oscillations per unit time. So if you remember, right, we said there are 5 oscillations in what? In 2 seconds. 5 oscillation in 2 seconds. That means the frequency is going to be 2.5. And what is the unit for frequency? It is hertz. Basha? So now at this point, we have some relationships or some equations to find the frequency. One of them, Basha, whenever frequency is mentioned at this point now, there are 2 methods or 2 ways to find the frequency. One of them, Basha, we can say frequency, it is equal to 1 over the period. Basha? And if you want to find the period having the frequency, you could just swap their places. That's first. There's another way to find the frequency. If you're given the number of waves or oscillations or vibration, you can say the number of waves, Basha, or oscillations if you want, just call them all. The number of waves or oscillations, or you can say vibrations. These are all correct. Vibrations per unit what? Per unit time, or how long does it take, Basha? So if you're given the period and you're been asked to find the frequency, this is the one that, or the equation you need to use. But if you're given the number of waves or oscillations, and then over time, then you can do that as well. And by the way, we also have a WSAT question. All right, they'll ask you to find how many waves or vibrations or oscillations will there be in a specific or in a period of time, in a certain, let's say, time here. So what do you have to do here? You'll have to find the period. There is another way, by the way, Basha. Once you find the period, now you can find the frequency, Basha. Then once you have the frequency, right? Given the time is also given, then you can find this one just by multiplying this or cross multiplying this too. Yalla, let's not forget this point here. By the way, frequency here, it is equal to 1 over what? 1 over period. But don't forget, let me rewrite this one perhaps. But frequency, it is equal to 1 over period. But frequency, it is measured in hertz, but this hertz, it is equal to 1 over second. This second can also go up. We can say hertz, it is equal to second negative 1 as well. So this is also possible. So this is a unit, equivalent unit for hertz, but the hertz is the unit for frequency. Don't forget this one here. So what happened if I cross multiply this one, by the way? Frequency times the period must equal to 1. Okay? You will need to use this relationship if they tell you, for example, again, if the period increases by this amount, what will happen to the frequency, or vice versa. And if the frequency increased by this much, what will happen to the period? So whatever, for example, the numbers are given, you can use them, and then just to find how much or by what factor will the other factor change. So this is also possible. Basha. So what else, or what is left to mention here? So remember, we said period, it is the time it takes a complete cycle to occur, measured in second. But frequency, we said it is the number of cycles or vibrations or oscillations per unit, time measured in hertz. Frequency, it is 1 over period. Again, if you want to find the period having the frequency, you could just change or cross multiply, swap their places, and you can do this. And of course, you can do this one also. So now at this point, you have two methods or two equations to find the frequency. We said if you're given the period, you'll use this equation. But if it mentions the number of waves or even asks for it, then that is the equation. You need to use that. Now at this point, we'll have to something that is very important. And what is it? So, and that is, we can say how many amplitudes are there in one full oscillation, because every amplitude is a distance, right? So watch this. We have a pendulum, Basha. This pendulum is, this is the equilibrium. And let's say that this is the equilibrium position, or maybe we could start over there. It doesn't matter which end you start, Basha. This is point A. So sorry. We said if you let go of this mass, it is going to oscillate. Do you agree or not? Yes. But before that, so it is going to oscillate to point B, assuming that this is point B. But here's the thing. We said this mass, it is at maximum distance from equilibrium position. And guess, what did we use to call this maximum distance? Didn't we call this one amplitude? Yes. So here's the next thing that I need you to remember. For this mass to complete one full oscillation, it has to go all the way to this end and then come back to the same point. In other words, if we start from point A, it has to go all the way to point B, and from point B it has to go back to point A. That'll be one full oscillation. And you've learned that, right? And this is the equilibrium position. You can say this is the equilibrium. Oh, we could have just drawn this one right below this point here. Okay, let's just make these ends same so that you don't complain. So this is the equilibrium position, but watch this. Didn't we say the maximum or the maximum displacement from the equilibrium position? Don't we call this one amplitude? Yes. So this is my point. In order for this mass to go from point A all the way to point B and come back, how many amplitudes does it cover? What does that mean? And how many distances or maximum distances does it cover? Basha, from point A or from this point to this point, isn't that one amplitude? Basha. Now from equilibrium to point B, isn't that another amplitude? Yes, that is 2. And then, now from point B back to equilibrium, that is 3 amplitude. And then from equilibrium back to point A, that is going to be 4 amplitude. In other words, for the mass from point A to go to point B and then back again, it covers 4 amplitudes. Basha, it covers 4 amplitude. So that is in one period, right? So based on this, we can make an equation here. We can say in every period, Basha, there will be 4 amplitude. What do I mean by this? Consider this. If every amplitude, watch this, if every amplitude here, if it is 10 centimeter, what is the total distance that is traveled by this mass? Watch this. Good man, if every amplitude is 10, so that'll be from point A to the equilibrium, that'll be 10, that is 20. And then back to equilibrium, that is 30. And then back to point A, that is going to be 40. In other case, this is 10, right? This is 10. So 10 plus 10, 20 to go. And then 20 to come back. So that is a total of 40 centimeter traveled by this point, or you can say this mass of the bob of the pendulum. But remember this. So once again, in every period, there will be 4 amplitudes. Amplitude you could just multiply. So we could do that too, right? In a time that is equal to 1 period, there is 4 amplitude. If every amplitude is 10 centimeter, you just multiply them. 4 times 10, that is going to be 40 centimeter. This is how much distance traveled by the pendulum. Basha. What if it says how much or how long does it travel sorry, not how long, how far, what is the total distance that is traveled by the mass or the bob of a pendulum in a time that is equal to 2 period. Basha, but man 2 period يعني تسع. In every period there is going to be 4 amplitudes one, yeah? So 2 period it is going to be in a time equal to 2 period. Basha, good man, in every period, so 2 times, in every period there is 4 amplitude one, yeah? So in a time that is equal to 2 period, it is equal to 8 amplitudes. So now, amplitude the hertz and you just multiply one, yeah? So if the amplitude is 10, just like the example we said, we'll just say 8 times 10, it is going to travel 80 centimeter. But remember, that is for the distance. Even though displacement, I don't think they'll ask you, but what if they say, what is the displacement in a time equal to 1 period? Baba, again, displacement is a vector quantity. If it is going to the left, that is going to be negative, for example, one, yeah? So let's say if 10 and 10, it's going to be negative 20. If it goes from this point back to point A, that is going to be what? That is going to be positive 20. And you add, once you add these two together, so the displacement, it is going to be 0 here. Because you've learned that displacement, it is the shortest path one, yeah? You can say between 2 points. But if the object goes back to the same point, hey Basha, what is the displacement? Isn't that the same as if the object haven't traveled or haven't moved at all? Yes. What is the displacement traveled? No matter in how many periods, the displacement is 0. If it goes back to the same point, by the way. But if it is distance, we'll just combine how many times it goes back and forth. But the most important thing here to remember is that in every period, there are going to be 4 amplitudes. We'll just multiply by that. For example, in a period, 1 period, 4 amplitude, 2 period, 2 times 4, one, yeah? And then 3 period, 3 times 4 amplitude, and on and on. The amplitude could be any number. You just multiply, Basha. What else do we need to know? I think that is the idea that I was about to tell you. There's more things actually. What if it says, how many times, this is like, what is 1 full cycle? Imagine we're considering starting from point A and then to point B, back to point A. We said this is 1 full cycle, yes? Full cycle. What if it says, how many times does a pendulum passes through the equilibrium in 1 full cycle? Don't get confused with this one here. In order for let's say for this mass to go from point A to point B, it is passing through the equilibrium once, right? And then if it goes back, it is passing through the equilibrium another time. So if it ever mentions how many times does it pass through the equilibrium, in 1 full cycle, it passes through the equilibrium 2 times. Why? Because 1 time for going, and then the other time is for coming back. That'll be passing through the equilibrium twice in every cycle. All right? And then there is also, remember this, in Wizari, they might tell you this. We have a pendulum that passes through the equilibrium position 20 times. How many, or how do we know how many waves or how many cycles does it make? All right. So once again, we said in 1 full cycle, it passes 2 times through the equilibrium one, yeah? Basha. If it passes, let's say, through the equilibrium 20 times, right? How many full waves is it going to be there? You could just use this one or make this one unknown here. So there's a question mark. And then, of course, you're going to divide by 2 here. So we can say the number of full waves, if you want to call that, or the number of waves, the number of cycles. We'll say the number that is passing, all right, through the equilibrium, Basha, passing through the equilibrium divided by 2. So 20 times passing through the equilibrium, divide by 2, that means there are 10 full waves, Basha. The same thing can be asked regarding the amplitude. If an amplitude is, if a pendulum is, pendulum man here, it is covering, let's say 12 amplitudes, Basha. 12 amplitudes. We have a pendulum, Basha. This pendulum, it is covering 12 amplitudes. How many full waves are there, Basha? We said that, okay? So in order to do that, we know that in order to make 1 full cycle, it covers 4 amplitudes, one, yeah? So if it is covering 12 amplitudes, can we just divide by 4? So in this case, the number of waves, let me write it below, the number of waves, Masha, if the number of amplitude is mentioned. We know that whatever, let's say, or no matter how many times it is passing, Masha, we can say number of times passing through the, number of amplitudes that is making, Basha, number of amplitudes covering, Basha, divided by 4. So we said it is traveling 12 amplitude, one, yeah? But every 4 amplitude they got the 1 wave, so in this case there will be 3 full waves. Just an idea. I don't think it will be in Wazari, but just in case, yani. All right, now let's go back to, no, it's not this one here. So these were what we were talking about. Remember, in one full cycle, there's 1 amplitude to the equilibrium. That is 2 to go, and then there was 2 to come back, so it's going to be a total of 4 in here. This is the equilibrium position. This is going back and forth. There's one more thing I would like to tell you, and then after that, we'll go to the other page in here. So what is this thing right here? If we said that the amplitude of a pendulum, it is measured using an angle theta, yes? But if you're given the length in here, can you find the distance or the amplitude in meter? Okay, what is the amplitude in meter in here? Now, you know that this is we can see that there is a right angle here, and this is a triangle. Is that correct? Yes. So by knowing this angle, whatever this angle is, let's say this angle is 30, okay? And you're given the length as well, so we could say the length is 1 meter, Basha. Can you find the amplitude, not in angle, let's say not in degrees, Basha, in meter? The answer is yes. And once again, we want this distance, right? Then this is the angle. Can I call the length hypotenuse in here? Yes. So we have 3, like functions, sine, cosine, and tan one, yeah? Which one of these would allow me to find the opposite? Because this is the angle, this would be the opposite, right? So of course, we can use sine theta. We know that sine theta, it is equal to what? It is equal to opposite, all right, divided by the hypotenuse, we can say. But the opposite here represents the displacement, or you can say the x, which is the amplitude in here. And then the hypotenuse here, it represents the length of the string in here. So now we can say the maximum displacement, or the amplitude if you want to call it, it is equal to what? It is equal to L times sine theta. In other words, if you have the angle and if you have the length, you can find the maximum displacement from the equilibrium position in meter here. So now this amplitude, whatever the answer is, it is going to be measured in meter. This is how, now based on this, we can say the amplitude for a pendulum, it can be measured both in theta, in radian, or it can be measured in meter as well by using this sine function. All right, now going back to where we left, we have a question here. Oops, that is the second time. All right, we have this question here. What does it say? It says, we have a pendulum, Basha. I want you to underline these keywords for me too. It says, what is the total distance? It is a distance, not a displacement, traveled by an object moving back and forth. Let's just, okay, now we can write on that. It is moving back and forth. I should have given this enough time for this to disappear. Okay, we'll just use this now. All right, it is moving back and forth. Don't forget, it says in a simple harmonic motion. Watch this. In a time interval equal to, it is period. We need this part here. Basha, when it is amplitude, it is equal to just A. This amplitude here, they set A here. It could be any number, by the way. It could be 5 centimeter, it could be 10 centimeter, but that is not our concern in here. what you need to know, the question says, what is the total distance, all right, in a time equal to 1 period? Basha. We said if a pendulum is swinging back and forth, just like this one here, in a time equal to 1 period, what does it mean 1 period? That means starting from this point, going all the way to this side, and then getting back to the same point, right? Getting back to the same point, that is 1 full period. Basha, good man. So the question says, what is the total distance? So we can say the total distance here in a time equal to, it is period, right? And we said that in 1 period or in every period there are 4 amplitudes, yeah? So now, how long, or what is the total displacement now? It is going to travel 4 amplitudes in here. So we'll just keep the amplitude because it says amplitude. Basha, what if the question says every amplitude it is equal to 10 centimeter? All right, in this case, 4 times 10, that is going to be 40 centimeter or 0.4 meter. That is also possible. It could be any meter. What if next time they say in a time it is equal to, let's say, 2 period, Basha? 2 it is period, yani 1 period. What if they say in a time equal to, let's say, 2 periods? Okay, in that case, of course, we would have said distance is equal to 2 period, yes? And we know that in every period there's 4 amplitudes. So 2 times 4 amplitudes, right? So that is going to be 8 amplitudes. Amplitude you just multiply. What if they say in a time equal to half of it is period, half? Basha. We'll do the same thing, right? In a time equal to half of it is period. This is half, and this is a period, yes or no? We said in every period there is what? There is 4 amplitude, right? Should just replace 4 amplitude there. Now, this 4 and 2 simplify, so it is going to be 2 amplitudes in here, and that makes sense. If it is a time equal to, you can, by the way, you can start at any point here. This is perhaps not a very great choice in this case here, because we always used to start from point A all the way to point B and back to this. But does it matter which point you start now? If you start from point A, you go to point B, you go back to point A, that is half a period, yeah? And then you go to point C and then back to point A, that is 1 full cycle. That is not the major thing to worry about. So, what if the question, remember, this is our pendulum, we're starting at point A all the way to point B. What is half a period? Half a period, it is starting from point A all the way to point B. How many amplitudes are there? 2. So there are 2 amplitudes in half a period. What if the question says in a quarter? What is the total distance traveled in a period, let's say in a quarter of a period? Quarter of a period, quarter, you know that. Quarter is 1/4, yeah? Of a period. So good man, in every period there is what? There's 4 amplitude. Yeah. So this 4 and 4 simplify. So the total distance in a quarter period, it is going to equal to just 1 amplitude in a quarter. When we say quarter, that is just this much, starting from point A to equilibrium position. Also, it could be any number, any period. All right, and so this is what it is. So the total distance for 1 full swing, that is going to be 4 amplitudes, yeah? And that is what it is. One question, what if it says, what about half a period? Good man. Just use the equation, yeah? So that is, you can use what I just told you as an equation. My total distance, half a period, so half t. In every period, don't forget there is 4 amplitudes. So just replace this with that, then you get half a period. We've added one more thing. What if it says, what is the distance traveled of a simple harmonic motion in a time interval equal to 2/8 of its period? Basha, this is just a number, I'm going to like to confuse you just to see if you know or not. So 2/8, what does 2/8 means? That means 2 divided by 8 of what? Of its period. Basha, just multiply by period. So that is the total distance, 2/8 of a period. Yalla day. 2/8 times, we said in every period there is what? 4 amplitude? Yalla, simplify. That is going to be 1/4. This 4 and 4 cancel out, so it is just going to be 1 amplitude. It's the same as saying 1/4, right? That's just, like for fun, just to see if you know this or not. Yalla. Let this study tip be the last thing perhaps for this session here. We've mentioned earlier that a pendulum passes through the equilibrium 2 times or twice in every complete swing. Don't forget this. The next thing says to find the number of swings, oscillations, waves of a pendulum, if they gave you the number of times it passes through the equilibrium, you can use this equation. It says number of oscillations or number of waves, no difference. How many times does it pass through the equilibrium? Divide by 2, because in one full cycle, it passes through the equilibrium 2 times, right? So 1 to go, this is the equilibrium, 1 to go, and 1 to come back. What if the question says to find the number of oscillations of a pendulum if, let's say, given the number of amplitudes or how many amplitudes the pendulum makes? Okay, we'll divide the number of amplitudes by 4. For example, it says a pendulum covers 20 amplitudes. Basha, how many waves does it make? We know that in one full wave, it makes 4 amplitude. Kata 20 divided by 4, we can get 5 full waves, oscillations, you can say. And don't forget this, when it says cycles, waves, vibrations, number of shakes, all these means the number of waves. So now you can recognize this. Okay. Now, this would be the end of this session, all right? Inshallah, next time we're going to start with these questions. These are easier. That'll be for next time. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.